the assessments. So we spoke about the second assessment. These are the 3 questions. A question about the referencing style. It's in the Harvard style, which most of you are most probably very well used to. If there's any questions or about that specifically, then I've updated the website. So there's a link now to the university statement on how you should reference in the Harvard style. And I've given a Harvard style example in the template that I would like you to use. So the T-shirt for today is what powers the perfect storm, because power seems to be important. And it's in that context, and it's not just about power, that the second assessment needs to be considered. And actually, there's one more thing I need to talk about this second assessment. Somebody asked me about word limits. There's a maximum 1,000 words. That's in order to make sure that you gauge the amount of effort that you need to apply for this particular assessment. There's no real minimum. Well, there is a minimum number of words I would suggest for each question. That's 200. So just be sure that you write at least 200 words for each question. And then there's a certain degree of flexibility as what you do with the rest of the words. And yes, each answer is going to be worth about 1/3 of the mark, but there is some wriggle room. I want to give you the opportunity to write something really interesting in one particular question, let's say. So you've sort of got to cover the bases of the other ones, but if you do a really, really good job in one question, then I want to give you the opportunity to maybe throw you a few extra marks for that. Only seems fair. But there's some wriggle room. Don't go mad. Okay. If you've got any questions about that, then I'm more than happy to talk to you about it. Give me some draft questions, or you can show some draft question answers in class, and I'll go through it with you. That's absolutely fine. So, power. I've been talking about it in terms of coordination of resources and money, but really, it may be all about power. And some people do make this argument. They make it a lot. The global challenges, the perfect storm, look, it's just an issue about power. Because if we had effectively unlimited energy, then we wouldn't have many of the global challenges that we do. We wouldn't have this pressing perfect storm, which is bearing down on us in the few decades. Why? Well, let's imagine you would be able to transition to this solar future or this renewable future, or maybe even, a biofuel future. We could produce abundant amounts of energy with next to zero environmental cost. You can grow as much food as you want. So hydroponic plants are already in operation. Hydroponic systems are where, you most probably know, you've got a plant and you don't plant it in the ground, you plant it in some kind of liquid medium, which these troughs, and through that you circulate all the things that a plant needs in order to grow. So, it's potassium, it's phosphorus, it's nitrogen, all the other bits and pieces. And that takes lots of energy. I mean, you're going to assume you're going to plant it somewhere where there's not lots of sunlight. But if you've got unlimited energy, if you can secure, you can get hold of all the necessary nutrients and requirements for the particular plants, because you can mine it, you can transport it, then you can grow not unlimited amounts of food. There are upper limits of the amount of food or biomass you can produce on the surface of the Earth, something I'll talk about next week. But you could certainly make sure that nobody goes hungry. If you've got unlimited amounts of energy, then you get away, or you can escape the resources problem, because you can effectively recycle everything. You can close that loop. So at the moment we've got resources which we exploit, and we consume materials, whether it's iron or nickel, and then we make them into things, and then typically what we did at the end of their useful life is we put them in a tip and we threw them away. There are now millions of tons of gold in tips. There are millions of tons of useful metals that we will need, or that we even currently do need, in order to produce electronic components. So what's going to happen in the near future is that tips will become mining sites. You'll have urban mining. People are going to go back and revisit these tremendous stores of stuff that in previous generations we thought was rubbish, but now we actually realise, because we're depleting the easy to get hold of natural resources, we need to go back and recover the stuff that we threw away. And that's going to need energy. It's going to need energy to, build the mines, dig the mines, purify the material, get hold of that matter again. So in terms of a recycling loop or a feedback loop, the more energy you've got at your disposal, you can make sure you recover the stuff that previously was being lost back to the Earth system, really. And over geological times, all this stuff, if it wasn't recycled, would end up in rocks and be subducted back into the Earth's interior. So we're trying to keep hold of it for as long as possible. So if we had unlimited energy, then we wouldn't have a resource issue, because we could recycle pretty much everything. So power, generating energy, is very important. And I want to describe that or explain a few concepts in terms of energy with a bicycle. So who cycles? Who's got a bike? Anyone? But I guess lots of you have actually been on a bicycle. Right. So you're pedaling along, and let's imagine you go from point A to point B, and that distance that you've cycled is proportional to the amount of work that you've performed. So if you're pushing those pedals, you're doing work. And the amount of work that you do is proportional to basically just how far you've gone. So the further you go, the more work you do. As you know, when you try and cycle up a hill, it's going to get harder. You have to put in more work. You're typically going to go slower as well. So now the amount of work that you do isn't just proportional to how far you've gone, but in a sense of how high up you've gone. Now, the greater the slope, the steeper this hill is, then the more power you're going to need to get up it. Some of the hills in Southampton, maybe around its environment, if you go into the South Downs, certainly, you can't really even get up them on a bicycle. You'd have to stand up out of the saddle, you'd have to really push down with every particular pedal stroke. So you need to generate more power to maybe even get to the same kind of distance. So power is what we mean when we're talking about a rate of energy use. So how much energy you, on your bicycle, are using every single second. And these are just the units. So SI units, we want to make sure that we're talking about the same sorts of things. And so I'm going to introduce a couple of the standard units that we use when we talk about power, when we talk about energy. So you know what a calorie is? Or rather, you most really know what a kilocalorie is, because kilocalories are the things on the sides of your Snicker bar that makes you feel guilty about eating it. So 1 calorie is the amount of energy that's required to heat 1 cubic centimetre of water by 1 degree Celsius. So imagine you've got a little cubic centimetre of water, which most probably wouldn't hang suspended in the air. It would be in some kind of medium, and you've got some kind of flame. Then assuming all the energy from that flame went into that little cube of water, then by the time that cube of water is increased by 1 degree Celsius, we've consumed a single calorie. Where do calories come from? Well, some bloke. But the unit of energy that we use now is called joules. Where do joules come from? Some bloke. All we need to know is that 1 calorie equals 4.2 joules, right? So there's a certain amount of energy units, and we typically now talk about joules. So that's the amount of energy, right? The amount of energy that had to be, in a sense, transferred from the combustion of that flame into that cube of water, which then you could detect by monitoring its temperature. But that's not a watt. A watt, W-A-T-T, where does watt come? Guess what? Some guy is about the rate of energy consumption, or maybe the energy transference, or how energy is moved around. So imagine you've got a 100-watt bulb, and these are the good old-fashioned incandescent bulbs you're not allowed to buy anymore because they are just grotesquely inefficient. But a bright bulb would be on the order of 100 watts. Nowadays you can get a 10-watt energy efficient bulb, and those kind of incandescent type bulbs, and a 10-watt energy efficient bulb is most probably equivalent to the old-fashioned 100-watt incandescent bulb, but the principle's the same. Basically you've got a bulb, and this is my crude representation of a wire, which is part of an electric circuit. And when you generate an electric current, what you're doing is you're pushing electrons through a piece of wire. So as those electrons whiz past that wire, which actually they don't go very fast, but they do move, okay? You generate a current, and as those electrons are moving, they kind of go around this circuit, and there's a high resistance piece of tungsten wire there, and that gets really, really very hot. And as it gets really, very, very hot, it emits a lot of light. It also emits a lot of heat, which is why they were so horribly inefficient because mainly you want a light bulb to make things light and make things warm. Anyway, so you've got electrons flowing through a piece of wire that make that light bulb go up. And that was direct current. The kind of current that we've got in our domestic and even here is alternating current, so the electrons move backwards and forwards. But there's a flow of electrons through some piece of wire. So if you've got a flow of something, you can think about the electrons as flowing pretty much like the flow of water. And when we talk about electricity, things like current is used, the force of that flow. But you can imagine if you've got some kind of wire here where there's electrons flowing through it, then as you increase this tap, as you let out more electrons, as they run faster, then the more electrons that are moving, the more energy which is being transferred every second, then the more watts that you've got. So 1 watt is just 1 joule per second. That's all a watt is. A watt is a rate. It's the amount of energy that gets consumed per second. So when you're cycling on a horizontal piece of land, on a reasonably functioning bicycle, you'll be generating a certain amount of power. Let's say you're maintaining a certain speed, so you're not increasing, you're not accelerating, you're not decelerating. And they could monitor that power output. They could put you on a special static bike and they can see how many watts of power you're generating. Now, in order to maintain that speed, as you're going up a hill, you're going to have to generate more power, so your watts will increase. Now, one of the confusing things about energy and the way it is costed and charged, or billed certainly, is they don't bill you. Utility companies don't bill you for the amount of energy that you've used in terms of joules. They don't say, last year you used this many joules, right? So they use these things called kilowatt hours. Anybody looked at an electricity bill? Does anybody pay an electricity bill? Yeah, it's quite a depressing activity. But anyway, what they do is they charge you for kilowatt hours. And so what that means is that there is an actual amount of electricity that you will consume. So you imagine there's a flow of electrons through there, and I'm consuming that by running my television or my fridge or something else. And over a period of time, that fills up. Now what they do is they bill it in kilowatt hours, which is, if that rate is now not just 1 watt, but 1,000 watts, and I run that for 1 hour, then I will have a certain amount, okay? So that's what they bill you in. So that's how you end up getting from a rate, which is a watt, which is something, a certain amount per second, to a total amount, because a certain amount per second times a period of time. Why they do it like that, I guess somebody decided at some point in the past. Anyway, the point of that little diversion is watts can be very large. We consume tremendous amounts of energy. So here we have 1 watt over here. They bill me and they bill you in things called kilowatt hours, which is 10 to the 3, which is thousands of watts per hour. But then you're going up to megawatts, megawatt output, and gigawatts, and then even terawatts. So this thing here, this is an offshore wind turbine, and that is a 5 megawatt wind turbine. So my consumption of electricity last year was about 2 megawatt hours, so 2,000 kilowatt hours. So basically, I consumed the output of that wind turbine, its total output, for about 30 minutes. But I would just stagger that over 365 days a year. That's not particularly high, and it's not particularly low, but that's just my contribution to the consumption of our global energy use. So our global energy use is this. It's 16 million watts. So that's 16 terawatts. So when it gets to these numbers, these very large numbers, we are talking about terawatts. So what this means is that every second of every minute, of every day, of every hour, our global industrialized civilization is consuming 16 million joules of energy per second, on average. Sometimes it goes up a lot in the UK. When there's an ad break in Coronation Street, everyone puts their kettle on. Sometimes it goes down when we all go to sleep. There's tremendous variability in our energy consumption, which makes managing something like the national grid so very difficult, because you've got to always anticipate demand, you've got to have enough generation on hand. But it's a staggeringly large number. So part of my motivation today was I wanted to give this number some context. So what is a watt anyway? But there's another way to give it some context, and that is, how does that number feature with some other rates of power in the Earth system? So back in 2011, I did a bit of work, and then as a part of that work, we estimated the amount of power that was being generated by different Earth system processes. So mantle convection, you know, there's, even though the mantle is a rock, it's under such pressure, it behaves like a kind of viscous soup that moves around. Kind of mountain forming, continental uplift, weathering, sediment transport. And these are big numbers, you know, these are all terawatts. But if you look at human activity, 15 terawatts, our appropriation of energy in the Earth system is actually larger than global rates of mantle convection, or even maybe sediment transport, you know, the transport of rocks and stuff from the land into the sea. It's a very, very large proportion. But you'll see there are even larger ones. There is the total biotic activity, so this is all land life, and this is all sea life. And they're even larger, you know, 264 terawatts. It's much bigger than any kind of geological process. And bigger than anything else is its atmospheric circulation. So why are those numbers so big? Why does the Earth system generate so much power in moving basically water and air around on the surface of the Earth? And why does it generate so much power from things, basically, that's primary production, that's photosynthesis on the land, and that's photosynthesis in the sea? How are these numbers so large? It's because of the sun. These are solar-powered processes. So, if you were to take an average square metre on the surface of the Earth, then heat comes out of that. That heat is produced by radiogenic decay, radioactive particles, mainly in the crust, and as they decay they produce heat. There's also quite a bit of fossil heat, so heat left over from the formation of the Earth 4.5 billion years ago, and it's not a very large amount, it's about 0.8 watts per square metre. The thing is, it's not uniformly distributed. There are some places where there isn't really any at all, and there's some where there's quite a lot. So, does anybody know what this is? Yes, it is also IKEA, but that is a geothermal station. So you may not know, but there's a geothermal energy plant in Southampton. It's been going since the 1980s. They drilled a borehole and they found there was kind of a hot aquifer. And so what they do is they pump down water, and that water gets heated up, and they use that for district heating and power. So they pump that hot water around. I think there must be about 1,000 businesses or maybe even residential units which are being heated by that facility, and they're also able to generate a certain amount of power, because if you get heat differentials then you can run a heat engine and you can generate electricity. Some countries, you know, Iceland, have tremendous resources of geothermal energy. They're very, very concentrated. But globally it's just not a very big player, and ultimately it's geothermal heat which drives all geological processes, the convection of the mantle, the movement of the tectonic plates, earthquakes, mountain forming, all that is driven by the heat which comes out from the interior of the Earth. At the top of the Earth's atmosphere, on average, there's 1,300 watts per square metre. I mean, that's at the top. By the time you get down to the bottom, it's a bit less, and there's other kind of absorption processes. But if you're interested in not just how much energy can be produced from solar power, but also what that energy source does to the Earth's hydrosphere, how it affects the atmospheric circulation, then it seems reasonable to look at this number here. So that's much, much larger, you know. Over 1,000 times more energy hits the top of the Earth from the sun, something that's 93 million miles away, than comes up from within the interior of the Earth. And so basically the Earth is a big heat engine, in that heating, or that amount of energy that falls down on the Earth, isn't uniformly distributed either, just like geothermal heat. Most of it comes around the equator in the tropics. So you've got a hot middle bit and you've got the cold top bit, and as that heat moves around, that's what drives the Earth's climate. That's what drives the jet streams. That's what makes the climate in the UK what it is. That's why we don't have a completely frozen North and South Pole or higher latitudes, because that heat moves around. So what we've done in a global context is one of the reasons why we can generate 16, 15 or 16 terawatts of energy is because not only can we access that solar power directly, we can do it by generating a certain amount of electricity, proportionally not that much. More importantly is that we can get hold of solar power by consuming plants that that transfer solar power into biomass. But more importantly is we've been digging up fossilized sunlight. So millions of years ago, plants would have harnessed that sunlight, made sugars and produced biomass, fixed carbon, and that carbon got fossilized and turned into coal, gas and oil, and we've been digging it up and then burning it. And that's been the thing that has largely, over the last couple of 100 years, powered our industrializing civilization, which is why we're having such an effect. So, has anyone come across this term called the Anthropocene? Okay, so I'll talk a little bit more about this next week, but the Anthropocene has been the proposed new geological period that we are living in. We've become, Homo sapiens, a geological force. So there's going to be records of our activity in rocks. So, if we had unlimited, abundant, no environmental cost power, then many of the elements, or maybe even all the elements of the perfect storm would kind of disappear, wouldn't they? Because climate change is being driven by our combustion of fossil fuels, but we could transition to a low carbon future, that's all right. So that's the energy problem solved. You've got your food problem solved as well, because you can grow as much crops as you want, because you can recycle, you can sequester any minerals that you need. And water demand, well, if you've got unlimited energy, you can run unlimited numbers of desalination plants. So some places in the world, the water that they drink and they use for agriculture is desalination, so they take salt water and they turn it into fresh water. But you can't do that at a global scale because it consumes so much energy. So power. Power is important. And power is important in this context too. Because we have sufficient energy and resources and food right now. But the reason we don't equally distribute those or sufficiently distribute those, or the reason we have certain challenges now and into the few decades and then further into the future is, in a sense, not just the ability to generate power, but then the ability to wield power or the application of power. Our current paradigm is one of international relations, so countries, national self-determination, representation at a global scale via this thing called a nation state. And some people would argue that that kind of formulation or that kind of structure just isn't particularly well disposed to solving global challenges. So it's not just a question of power in terms of generating power, producing power, but then how that power is actually wielded in a political context. Okay. Moving on. I goofed. I made a mistake. When I made the groups in Blackboard, I somehow, don't ask me how, managed to create them in a way in which you can't edit the group description. So when I asked you to edit your group description with your project ideas, has anyone been able to do that? Has anyone actually tried? Okay. Well, some of you did, and you told me that you couldn't do it. So somehow we need to get around that. So what I'm going to do, we're just going to have a break. And then in the break, I would like at least one of you to please boot up your laptop, log into Blackboard, find your group, and then see whether or not, I want to test whether or not you can actually change the description. But then what we're going to do is add something called a wiki item. It's like a note. So basically it's a way in which you can populate your group with some information about your group project. So before you disappear for a break, let me know about that. Some rules about group working. If you leave the theatre with your group, can you tell me where you're going to go beforehand? Because I want to come round and talk to you as we're all doing group activities. And please, can you be here no later than 11:35 so we can do a wrap-up? Right. So we're going to do have a break, and then we're going to do a group activity. There's two, yes? I'll come see you, yeah, that's grand. I'm hopeless with Blackboard, as you most probably fathom. So there's two things I suggest we do today. The first one is that you can work on your assessment 3, so this is the poster. I'm very keen to get going on this, because I know that the poster presentation isn't until after Easter, but I'm slightly concerned about how we're going to effectively work over the Easter period. So I want to make sure that everybody at least has a good idea of what we're meant to be doing. And in that instance, I want you to think about who do you want to look at this poster? What's that T-shirt message? So a single sentence, you know. So this is the poster about something, and then write out this kind of brief narrative or this little story that you want this poster to say. Or, if most of your group is aware, and there are some people are here who are the only representatives of their group, because there's a geography field trip and whatnot, then you may want to produce a first draft of this systems storm diagram, and I'll come round and I can talk to you about it. Or I can talk to you about some other aspects of assessment number 2. So if you've got a quorum in your group, I suggest you do the group activity. If you don't, then think about the second assessment. Tell me where you're going. Be back by 11:35, please.